Hello, this is the video submission for the San Diego State University Design Build Fly team for the 2021 competition. For this year, we are submitting our plane named Sherlock, which pictures and video can be seen below.
As you can see on this screen, this is the overall aircraft review drawing that was included in the report. When manufactured, Sherlock had a length of 60 inches, a wingspan of 60 inches, the fuselage laid 7 inches off the ground, the wings had a dihedral of 5 degrees, the V-tail had a dihedral of 30 degrees, and the sensor deployment mechanism was 19.5 inches from the tip of the plane. On the left, you can see the structural arrangement drawing included on the report. For mission 1, the overall plane had a weight of 8.65 pounds. For mission 2, the overall plane had a weight of 15.44 pounds. And in mission 3, the weight was 10.46 pounds.
For the flight control architecture, we're using a Spectrum DX9 that would communicate with our Spectrum 8-channel receiver in the plane, which would then control our 5 MKS DS6100 servo that were used for the ailerons, V-tail, and the front landing gear.
The system's layout included in this page shows the electronic and avionic components of our plane, including the report. Here we see notable components like the electronic speed control, the receiver, the batteries. For the propulsion configuration, we went with a Spectrum Avion 100 AMP-SC, 2 HV LiPos connected in parallel with the 80 amp fuses in line with the positive terminal, a 4632 new motor with a 16 by 12 APC electric propeller.
And for the payload mechanism control architecture, we have a Futaba receiver that takes signal from our ground station, and we use a Arduino Nano to power the receiver as well as control the microservo. The microservo acts as a switch to send data to the sensor itself, while the continuous rotating servo will control the spool that holds the wire that will carry the data as well as deploy and recover the sensor. And for the sensor control architecture, we have a 3-volt power supply in the form of an Energizer lithium battery and a Trinket MO, which is a microprocessor that will control the 3 LEDs to flash in sequence with the use of a transistor.
On your screen is the payload accommodation drawing included in the report. For mission 2 and 3, the sensor deployment mechanism was used, while in mission 2, 20 of the shipping containers were put into the plane.
For our final design, we considered multiple trait studies. Some of the things we considered were simplicity, speed and drag, volume, weight, and stability. The 3 that we considered were square, circle, and ellipse. From our trait studies, we found that the circular fuselage worked best for missions.
Our overall configuration trait study, we studied the conventional biplane, blended wing, and tandem wing configurations. And from those configurations, we determined the conventional arrangement to be best for Sherlock. We also did a similar thing for the tail configuration, but this time we studied the conventional T, cruciform, V, and H tails. And from these 5, we ended up picking the V tail as the ideal configuration for Sherlock. The last trait study that we did was to determine our airfoil. We did a study from 5 airfoils and ended up choosing the MH114 for our main wing.
Design improvements were made to both our fuselage and wing structures this year compared to previous year's planes. For the fuselage, we added a honeycomb core in addition to a carbon fiber skin. For the wings, we have a fiberglass skin in addition to 2 carbon fiber rods acting as wing spars. And finally, we have a 3D printed wing box under the fuselage floor with the purpose of transferring loads and preventing composite failure around the spar holes.
Mission 1 and 2, the plane was expected to complete the 3 laps in 1.60 minutes and 1.92 minutes. And for mission 3, the plane was expected to complete 18 laps in a 10-minute window.
And that's the end of our presentation. Thank you for watching.